Welcome to The Explainer. Today we're digging into temporal logic, which is the language computers use to reason about time. And we're going to tackle a really fundamental question that sits at its heart. When a system looks ahead, does it see a single, locked-in future, or does it see a whole tree of different possibilities?
All right, so here's our game plan. First, we're going to talk about why we even need a special kind of logic for systems that are meant to run, well, forever. Then, we'll explore the two big ideas about how to model time. After that, we'll put them side by side to see what they're good at. And finally, we'll get practical and figure out how you choose the right tool for the right job.
Okay, so let's set the scene. Think about some of the most important systems out there. The software running a massive server farm, the flight controls on an airplane. These things aren't like a simple calculator app. They don't just do a task and then shut down. They're designed to run continuously, always on, always reacting to what's happening.
And that presents a massive challenge, right? How can you be absolutely 100% sure that these reactive systems are always going to do the right thing? How do you prove that over a literally infinite amount of time they will never, ever hit some kind of catastrophic failure?
Well, the big breakthrough came from a computer scientist named Amir Punawalla way back in the 1970s. He introduced what we call temporal logic. It's a way of using math to make precise statements not just about what's true right now, but about entire sequences of events over time. And this idea is the bedrock of a technique called model checking, which lets us automatically test if a system's design actually lives up to the safety promises we make about it.
Now here's where things get really fascinating, because this whole idea of reasoning about the future forces us to a kind of philosophical fork in the road. It makes us decide what we even think the nature of time is. So let's take a walk down the first path.
In this view, you think of time as a single straight line. Any given run of a system is just one specific story. One event happens, then the next, all stretching out in a predictable chain into the future. It's kind of like reading a book. There's a beginning, a middle, and an end, but there's only one story on the pages.
This world, this single-story view of time, is the home of what we call Linear Temporal Logic, or LTL. Its entire purpose is to let us reason about things that happen along one specific timeline, one whole path of computation.
So what this really means is that LTL is the perfect tool for checking the entire journey of a single computation. You're making a big claim about the whole story, start to finish. You're essentially proving that no matter what, this specific story will always have a good ending.
Okay, let's rewind and go back to that fork in the road we were at. It's time to check out the other path and, this one paints a totally different picture of what the future looks like.
This viewpoint says, hold on, time isn't a single straight line. Instead, it's more like a branching tree of possibilities. At any point, the system could make a different choice or maybe get a different input from the outside world. And each of those things could send it down a completely different branch toward a different future.
And yeah, that right there is the world of Computation Tree Logic, or CTL. This logic is built from the ground up to handle this branching structure. It actually has these special commands called path quantifiers that let you ask questions about all these different possible futures at once.
So you see the shift. CTL is perfect for asking about the potential that exists from where you are right now. Instead of asking about one whole timeline, it asks things like, from this point, is there at least one path that leads to success? Or maybe more importantly, from here on out, is it true that all possible futures avoid a disaster? Okay, so we've got these two really powerful but really different ways of looking at time. How do they actually stack up against each other when you need to get work done? Let's put them to the test.
It really just boils down to your perspective. LTL takes this global view. It's like watching a movie from beginning to end and judging the whole thing. CTL, on the other hand, is like being a character in that movie who stopped at a crossroads, looking at all the possible roads ahead and wondering where they lead.
Now, this is where that philosophical difference has some huge practical consequences. As you can see here, each logic can say things the other can't. LTL is really good at expressing fairness, like a process that keeps asking for a resource will eventually get it. CTL is better for simple questions, like, is it even possible to get to a reboot state from here? But look at that last column, the complexity. Checking a property in either LTL or CTL is already really hard for a computer. It's what we call p-space complete. But if you try to combine them to get the best of both worlds, In a logic like CTL star, the difficulty just explodes. It becomes doubly exponentially harder, which can make it totally impractical for large, complex systems. It's a classic trade-off. You can have more power, but it's going to cost you a lot.
So all this brings us to the final and most practical question of all. With these two different tools in our toolbox, which one do we actually use?
So the bottom line is, there's no single best logic. It is a classic engineering trade-off. The right tool depends entirely on the kind of question you're asking. If you need to prove something about the entire run of a system from start to infinity, LTL is your guy. But if you need to know about all the possibilities that could unfold from this specific moment in time, then you're going to want to reach for CTL. It is all about balancing the power you need to ask your question against the computational price you're willing to pay to get the answer.
And in the end, this choice between a linear path and a branching tree isn't just some technical detail for computer scientists. It really gets at a fundamental question about what it even means for a complex system to be correct. Are we trying to verify that the one, single, inevitable reality of our system is a safe one? Or are we trying to prove that in a whole universe of possible stories, not a single one of them is allowed to end in disaster? It's a question that gets to the very heart of how we build trust in the machines that run our modern world.